Hello, hi, welcome to you all. I am Dr. Varalakshmi working as a faculty in the Department of Organic Chemistry, Sri Padmavati Mahila Vishwavidyalayam. Today we will discuss the topic on labile and inert complexes. See, the reactivity of metal complexes is based on the nature of the labile and inert complex. The ability of a complex to engage in a reaction that results in replacing one or more ligands in its coordination sphere is called lability, and the complexes in which the ligands are replaced by others are called labile, simply we can say. Whereas the inability of a complex to engage in such reaction we can term as inertness. It means it is reversed to that of lability nature. The inertness or lability depends upon the activation energy. If the activation energy is high, it imparts inertness, whereas low activation energy, it imparts lability. See, the inertness or lability can be determined by terms of delta G hash, that is free energy of activation. Delta G hash is equal to delta H minus T delta S. Here the stability of a complex is determined by free energy change. Whereas this is the another thing that delta G naught is equal to delta H naught minus T delta S. Here the delta G depends upon the reaction pathway delta G hash. Whereas delta G naught, it depends upon the difference in free energy of reactants and products. Next, we see the stability of complexes. Stability of complexes is depends upon kinetic stability as well as the thermal stability. Kinetic stability means the compounds, whether it may be labile or inert, we can say. Whereas in terms of thermal stability, the complexes can be defined as it is either unstable or stable. According to Henry Tamm, he described the complexes as labile if they have half-life of the reaction under means less than 30 seconds. If that half-life rate of the reaction is greater than 30 seconds, we can say that those are inert complexes. This labile and inert nature of the complexes can be determined or interpretation done by VBT theory. As we know that in the square planar complexes, always they shows labile nature, means all the four ligands are surrounded by to the metal, we can say that is simply square planar. All the square planar complexes are labile complexes, whereas in terms of octahedral complexes we can see whether the complex is labile or inert by means of either outer and inner orbital complexes and their stability. Kinetic behavior of outer orbital complexes we see now, and kinetic behavior of inner orbital complexes. For outer orbital complexes, the metal with the configuration D0, D1, D2, D7, D8 and D9 are highly labile, whereas D3, D4 are less labile. D0, D1 and D2, D5 configuration of metal complexes, they are highly inert. Both the high spin and low spin complexes of D0, D1, D2, D7, D9 and D10 and high spin complexes of D4, D5 and D6 are generally labile. Both the high spin and low spin complexes of D3 as well as the D8 and low spin complexes of D4 and D5, D6 are generally inert. This is the respective example with the metal with the respective configuration, means number of metals present in the d electron, we can say simply that is D0, D1, D2, D3, D4, D5, D6, D7 like that. With a D6 configuration here, if you see T2, G6, D6 means we consider as it is the low spin complex. Low spin means all the electrons are present in the T2, G6 only, then those complexes are inert. Whereas D7, D8, D9 and D10 they are labile. And the D6 complexes with the high spin, we can say high spin means first the electrons fill in the T2Z, then the followed electrons will be there in the AZ. Means total electrons for the D6 orbitals, electrons filled in the T2Z is 4, EZ is 2. Those complexes are inert. Example for this is aqua complex of manganese. Next, d-phi low spin complexes. D-phi low spin means all the electrons are present in the T2Z only. Means here phi means all the electrons present in the T2Z 5 only. This is the example with the respective inert. See here low spin means the metal ligand, here cyanide which is a strong field ligand. And d-phi high spin. High spin means both the means 5 electrons present either in the means both in the T2Z as well as with the EZ. First initially the electrons go into the T2Z. Later, the remaining electrons will occupy the EZ orbital. Those are, we can say, labile. Here, this is the example. This is a manganese complex is the example with a ligand, water as a ligand. Then D4, low spin complex. Low spin means all the 4 electrons present in the T2Z only. Those complexes are inert. Similarly, D4 with the high spin. T2Z3 electrons will be there in the T2Z3 as well as EZ1. Those complexes are labile. Example is chromium complex. D3 electronic configuration containing metal complex. Electrons in the T2Z3 only. Those are inert only. Similarly, D2 and D1. Labile and inert complexes on the basis of crystal field theory. According to crystal field theory, ligand field splits the d orbitals. The splitting leads to decrease in the energy of the system, whose magnitude depends on the number of d electrons present on it. If the crystal field stabilization energy increases by association or dissociation of the ligand, then the complex is simply labile. On the other hand, if it is inert means when there is a loss in the CFSE value. It means inertness means there is a loss in the CFSE value. If it is labile means there is increase in the CFSE value. Inert versus labile complexes. Inert complexes means, as we know that inert complexes are transition metal complexes that can undergo substitution reactions very easily. Whereas labile complexes are transition metal complexes that undergo substitution reactions very fastly or rapidly. The thermodynamic stability of the inert complexes, they are stable, and in terms of kinetic stability also they are stable, whereas for the labile complexes they are unstable. In the kinetic terms also they are unstable. What are the factors that affects the stability of the complexes? The first factor or criteria is based on the charge on central metal ion. Greater the charge on the metal ion, greater will be the inertness of the complex, since ML bonds are stronger. Why? Because means greater the charge means the electrons are closer to the metal, since metal ligand bonds are stronger. Second criteria is size of the central metal ion. Smaller the size of the metal, greater will be the inertness, because the ligands are held tightly by the metal ion. Next, geometry of the complex. Generally, 4 coordinated complexes are more labile than 6 coordinated complexes. Then with respect to d electron configuration, if electrons are present in the antibonding EZ orbital, the complex will be labile. The ligands will be very weakly bonded to the metal. Why? Because means electrons are present in the antibonding EZ orbital, so those complexes are labile and they are weakly bonded to the metal. Hence can be substituted very easily. In short, the complex contains less than 3d electron, it will be labile. If one or more EZ electrons are present, it will be labile.